Hello guys, welcome back to my channel Gamma Die Gamma. We're gonna just continue from where we were last time. So we're gonna be doing the limits on exponential functions. So the first identity we have is the limit as h tends to 0, a raised to h minus 1 over h, which is equal to the natural log of a. And more specifically, when you don't have an arbitrary constant but you have E, Euler's constant instead. We have the limit as h tends to 0 of e raised to h minus 1 the whole over h, which is nothing but the natural log of e, which is 1. So let's do our first example. The limit as x tends to 0 of e raised to tan of x minus e raised to x all over tan of x minus x. Now if you see the identity above, the power of e was the denominator, so we need to match that. So I'll have to add and subtract powers on top. So I'll have e raised to tan of x minus x plus x minus e raised to x all over tan of x minus x. So this thing matches with this thing. So I'll just use some exponent properties. So I'll just factorize e raised to x. We have e raised to tan of x minus 1 all over tan of x minus x. Now observe, as x goes to 0, tan of x minus x also tends to 0. So the identity above makes sense. It's satisfied. So this thing just becomes 1. This thing just becomes 1. All we are left with is the limit as x tends to 0 of e raised to x. When you substitute x as 0, we have e raised to 0, which is 1. So let's do a better example. Say we have the limit as x tends to 0 of 2 raised to x minus 1 all over the square root of 1 plus x minus 1. Now looking at the radical term below, so there's a square root and then there's a number outside which is added or subtracted. The best strategy is to multiply and divide by the so-called conjugate of that term, so that we can use the difference of squares identity and get rid of the radical. Basically rationalize it. So this becomes the limit as x tends to 0 of, bracketed this, 2 raised to x minus 1 multiplied by the square root of 1 plus x plus 1 all over 1 plus x minus 1. And let me just clean up the denominator for you. 2 raised to x minus 1 times the square root of 1 plus x plus 1 all over x. And now with the multiplicative properties of limits, I'm going to split this in two limits. The limit as x tends to 0 of 2 raised to x minus 1 over x times the limit as x tends to 0 of square root of 1 plus x plus 1, and this is just the formula, natural log of 2 times, when you substitute x as 0, this is square root of 1, which is 1 plus 1 is 2, so the final answer is 2 times the natural log of 2. So now we move on to limits on logarithmic functions. So the first identity, the limit as x tends to 0 of the natural log of 1 plus x all over x is just 1. So now let's apply the above identity in this example. The limit as x tends to infinity of x times the natural log of x plus a minus the natural log of x. Now if you see the formula above, there is an x in the denominator, so I need to somehow bring this x in the denominator. So I'll just rewrite this as the natural log of x plus a minus the natural log of x all over 1 over x. So anyways, x is going on top and multiplying with this entire thing. Now in the numerator, I'm going to use this property of logs. So say we have log of a minus the log of b. This is just the log of a by b. True for log of any base. Here it's just e, the base is e. So let's go ahead and apply it. The limit as x tends to 0. The natural log of 1 plus a by x all over 1 by x. Sorry, this is infinity, my bad. Now our original identity had x going to 0 and we have x going to infinity. So I would really like to do a change of variables. So I'll let t equal 1 by x. So when x goes to infinity, t goes to 0. So I'll just rewrite the question as t goes to 0 of the natural log of 1 plus a times t all over t. Now if you see the formula above, so the term in the x in the argument was equal to the denominator, and in the question we have an a in the argument, so I'll just introduce an a here, and to balance it out I'll have to multiply the a over here. And finally, as t goes to 0, at definitely goes to 0. The identity is satisfied and we are just left with a, because this thing just becomes 1. So I would like to do a last good question. So the limit as a approaches pi of sine of a over 1 minus a squared by pi squared. Now there are two things you should note. Firstly, all of our identities had the variable tending to 0, right? I mean even the logarithmic ones, the exponential ones, the trigonometric ones, all of them. And secondly, notice that we haven't used x. Yeah, mathematicians love their x's, but not in this case. So firstly, I wanted to write, make a substitution, change the variables, because I want, a is tending to pi. I want something to tend to 0 here, so that we can clearly apply the identities later on. So let a equal pi plus h, because when a approaches pi, h approaches 0, and we can totally write our question as the limit as h tends to 0 of the sine of pi plus h all over 1 minus pi plus h the whole squared by pi squared. And in case you were wondering how we were going to simplify the sine of pi plus h, let's draw where the angle pi plus h lies. So here we have all angles pi by 2, 0, here's pi, here's 3 pi over 2. So and since h approaches 0, h is really small. Pi plus h is somewhere like this. It's really small. So here all angles are positive. Here only the sine family is positive. Here the tan family is positive, and here the cos family is positive. You can remember it as all students take coffee. So anyways, so here, since only the tan family is positive, we have negative sine h. Limit as h tends to 0, the numerator is just negative sine of h over pi squared minus pi plus h the whole squared. And I'm actually going to bring the denominator on top. This becomes pi squared. Now I'll just bring the constants out. Limit as h tends to 0. So sine of h, I totally want to expand the bracket in the denominator. So we have pi squared minus 2 pi h minus h squared, because the pi squareds cancel out. And I want to pull the negative from the denominator out, and the negative cancels with this negative. So we just have pi squared times the limit as h approaches 0, sine of h over h times, I'll just bracket the first term. I'm going to split this up. Limit as h tends to 0. Since we factored out h from the denominator, we just have 2 pi plus h. Now this is just our identity straight off. This goes to 1. So we have pi squared times, and when we substitute h as 0, we have 1 over 2 pi. 1 over 2 pi. And 1 pi cancels out with this, and we just have pi over 2. So that's it for this video, guys. I'm gonna be starting with L'Hopital's rule next time. Many of you wanted help with that, and then I'll probably do continuity and differentiability, and then move on to derivatives. So in the meantime, please like, share and subscribe. Have a fantastic day. Thank you.